DYMOLA is capable of simulating dynamical systems over a wide range of domains, including mechanics, electronics and thermofluid analysis. The package browser to the left shows all the available building blocks. The thermal package contains two sub-packages. The fluid heat flow package contains components to model coolant flows, including pipes, valves, and boundary elements to prescribe pressure, temperature or mass flow. The heat transfer package has components such as capacitors to store heat, conductors, convection and radiation elements, with boundary elements to prescribe temperature and heat flow. Other packages also contain components with thermal interactions, such as transformers, friction, heated tanks, and more. Now, let's build a model of a cooling system using these components. Components are inserted through a drag-and-drop maneuver. First, we insert a heat-storing capacitor. We can easily manipulate the size and position of a component icon. By double-clicking on an icon, we can set the properties of a component. The heat capacity is set here. We now insert a heat flow component. By once again double-clicking the component, we will set a constant magnitude for the heat flow. When entering a quantity, we may choose the unit in which to specify it. Unit conversion is conveniently handled by DYMOLA in the background. There is also support for custom user-defined units. To connect two components, we select a port on any component, displayed as a square. The connection is finished by dragging it to another port. To model the capacitor's heat exchange with the coolant, which we are to add later, we use a convection component. We rotate the convection icon, and then connect it to the remaining components in the same manner as earlier. The convection component expects a signal to define the proportionality constant of the convection. This model will use a constant signal. The cooling system will be started off with an ambient component, which defines boundary conditions. After flipping its icon, its properties are edited to specify the pressure and temperature, while its medium is set to water. A medium defines quantities such as density and specific heat capacity. We would like to use the same ambient temperature at multiple points in the model. So, we propagate it as a global variable, Tamb. The next part of the cooling system will be a volume flow component. The mass content and flow rate of the flow source is set, and the medium is specified as water. We set the temperature equal to the ambient temperature, using the variable which was just defined. The coolant will be transported using a pipe with heat exchange. For the pipe, the medium is set to water, while we also define its mass contents, initial temperature, height difference, and a set of parameters to define the constitutive relation between pressure drop and flow rate. Another ambient component is inserted to set the boundary conditions in the other end of the pipe. As with the previous ambient component, the medium, pressure, and temperature are specified here. The newly inserted components are now connected to the rest of the system. Suppose that we want a visual output of the capacitor's temperature. For this purpose, a temperature sensor will be used. Finally, temperature is displayed with a show component. All that remains is to initialize the model. The capacitor's initial temperature is set in the same dialog as its other parameters. We will set it equal to the ambient temperature. If we desire to examine a component more closely in the model, we can do so at any time. Open Class takes us to a diagram view of the component. While viewing a class, we can conveniently switch to its coding layer or its documentation to retrieve desired information. By using the tabs feature, we can instantly return to viewing the model. So far, we have demonstrated how to build a simple model of a cooling system with constant inputs. Though modeling in DYMOLA supports general expressions which depend on time and state variables. This is a model from the examples library included with DYMOLA, showing the possibilities to model with a higher degree of complexity. Here, The thermal components are interacting with an electrical circuit and a controller. Let's go back to our model to simulate it. We will switch to the Simulation tab, and then enter the simulation settings. We set the simulation time to half a second. From here, one may also change the solver algorithm and solver tolerance. The Simulate button fires the simulation. An animation of the diagram may be displayed. We may choose different playback speeds for the animation. As it's played, note how the temperature display changes. In the browser on the left, the components of the model are listed. Expanding an item shows all quantities associated with that component. Every variable has a box next to it. Checking a box plots a variable, for instance the capacitor's temperature. Keep multiple boxes checked to plot several variables. Suppose that we're interested in the effects of different heat flow magnitudes. To change a parameter in the model between runs, we simply edit its value in the variable browser, and press the Simulate button once more. Note the different end temperature of the heat capacitor.